The chain rule is a very strange rule. In some cases it doesn't seem that it's required, but it is. Normally the chain rule is required when you have something that's raised to a power, like there might be a function inside of something and the power maybe is just a number, and maybe the power isn't squared, maybe it's to the 100th or the 200th, because I don't want to have to multiply it out and then find the derivative. Another way that it could be written is if you have like not necessarily a function like e to a power or e to a function. That would be a time where you would need the chain rule. If it's just e to the x, we know what its derivative is, but if it's e to the function, then that's a little bit different. Also, if you have like a number, I'll call it 3 to the f of x. It could be 2 to the f of x, 3 to the f of x, 4 to the f of x. Also, another way it could be written is maybe like a root of f of x, but that's sort of the same as this, because if you rewrote the root, it would be rewritten to the 1/2 power, or the 1/3, or whatever root that it is of. So let me show you what the chain rule actually is. It's kind of a different kind of process, and then we'll look at some examples about how to do it. So let's say that you have h of x equals f of g of x. And what this means is you have some function, but g of x is inside of the function. In this case, f of x was g of x. In this case, f of x was g of x, f of x, and f of x. Those are all really g of x. Those are all functions inside of a function. So what the rule says is that you find the derivative of f, and you leave g in there, and you multiply by the derivative of g. So what that means is that you find the derivative using the power rule, or using the exponential rule, or those kinds of rules. Then you go back and you look at whatever g was and you take its derivative. So let's look at some examples so I can explain how that rule is used. So here we have a function raised to a power. This is like the g of x. So to find the derivative, I start off, because it's something to a power, it's like x to the a, where a is a power. It just happens that x is a whole entire function. So I start off with the power rule. I bring my 100 down. I leave x squared plus 1 in there, subtract 1 in the power. So this is the first part where it says the derivative of f. Then I multiply by the derivative of g, and the derivative of g is the derivative of whatever was inside the parentheses, and that would be 2x. I do want you to go ahead and multiply here the 100 and the 200, so you get 200x, and then x squared plus 1 to the 99. So basically I used the power rule at first, and then I multiplied by the derivative of whatever was inside. Similar kind of problem here. I'm going to use the power rule first, so the 6 comes in front. Subtract 1 in the power. Then I multiply by the derivative of what's inside. So I multiply by the derivative of that. Derivative of 3x is 3. The derivative of e to the x is just e to the x. And then that's all I do. I don't need to multiply anything out, because 3 minus e to the x was not just a number. If it's just a number, multiply it by the 6. Otherwise, just leave it. Alright, this one looks different, but honestly, it's very similar to that last problem. We can rewrite this first as 3x squared plus 5x plus 2 to the 1/2. So now if I want to do the derivative, I do exactly what I did on the last two problems. Bring down the 1/2. Leave what's in there alone. Subtract 1. Then multiply by the derivative of what's inside. So I multiply by the derivative of 3x squared plus 5x plus 2. I get 6x plus 5, and you can leave it. The only time you need to multiply the 1/2 by what's at the end is if they're all just numbers, not a function. Okay, another similar kind of example, I would rewrite this as e to the x minus 4 raised to the 1/2 power. So then to find the derivative, I'm going to bring the 1/2 down, subtract 1, and then multiply by the derivative of the inside, which is e to the x. And then you can leave it. Alright, here's a different kind of problem. So one kind of problem that the chain rule is involved is something to a power. Another kind is where the power is a function. So what you do on this one, this is like your g of x. So you find the derivative of e to a power. Well, that's e to a power. You just leave the power. But then you multiply by the derivative of the power, which is 3. That's your answer. You can rewrite that as 3e to the 3x if you want, or you can just leave it. So the difference is the power is not just an x. The power is something else. And you just multiply by the derivative of that. Alright. So we have e to the power. The derivative of e to a power is e to the power. But then you multiply by the derivative of the power. So then I'll multiply by 2x. We haven't had to do this before because everything has always just been e to the x. Alright, number 7. Alright, because it's a plus, we're going to do these two things separately. And actually, you're going to use the chain rule separately. So the derivative of the first one, it would be e to a power, then times the derivative of the power. Well, the derivative of x over 4 is just 1/4, because that's the same as 1/4 x. And then on this one, it's like the first kinds that we were doing, where we bring down the 20, you do the power rule, subtract 1, and then multiply by the derivative of the inside, which is 1/2 x to the negative 1/2. The only thing, let's see here, you could leave this e to the x over 4 times 1/4, but I would go ahead and multiply these numbers, because there are numbers there, and make that 10. And then times x to the negative 1/2. You don't have to multiply that in anything, so that would be the answer. Number 8. Alright, similar kind of problem. It does have a 3 here, but I know that the derivative of e to a power is just e to a power, so I just multiply by the 3, leave it there. And then I multiply by the derivative of the power. Well, the derivative of x plus 1 is 1, so there's not anything much to do. It happens to be itself. Alright. Similar kind of problem, but this time it's 2 to a power. So the derivative of 2 to a power is natural log of 2 times 2 to the power. But then now there's one extra step because I multiply by the derivative of the power. And number 10, the derivative of 2 to a power is natural log of 2 times 2 to the power. One more step, I multiply by the derivative of the power. Well, the power is x to the 1/3, so the derivative would be 1/3 x to the, you do 1/3 minus 1, so it would be negative 2/3. And there's not really anything you can multiply together because none of those numbers are by themselves except for the 1/3. I know the rule's a strange rule, but I think you can do it. I basically gave you two types of examples of problems where you could use the chain rule. Here's some try problems. The first and the second one are very similar because it's something to a power. Number 3 and 4 are e to a power and 5 to a power. Just don't forget that you multiply by the derivative of the power or the derivative of the inside.